reversible reaction, reactants are converted into products and back again, and over time it eventually reaches an equilibrium. Now what is K? K is simply a way to measure when we reach equilibrium, do we have way more reactants or do we have way more products that are being produced? And so I've got this model right here that shows us how reversible reactions work. So there are going to be a bunch of molecules over here, we'll call those reactants, and they'll be green when they're on this side of the chamber, and they'll be red when they move over to the right side. This is a PHET simulation. Over to the right, I've created a K-ometer, which is going to measure our K value. So K is going to be the number of products divided by the reactants. At this case, we only have reactants on the left side, and so we have a very large number here, 100. And how many products do we have? 0. And so what's our K value going to be? It's simply going to be 0. So let me start this and see what happens to our K value. And so molecules are moving now from the reactant to the product side, from the product to the reactant side, but we basically have the same level on both sides, and so our K value is 1. Now as I tip it towards the right, we're getting more products, and so that is going to become a larger number up here, and so our value goes up to 3. We have about 3 times as many products. Likewise, when we pull it in the other direction, now we have way more reactants, and since our reactants in this case value is going to be around 75, products around 25, our K value is going to be around 1/3. Now this model oversimplifies a little bit because we only have products and reactants in this simulation. In a chemical reaction, you're going to have lots of products and lots of reactants. And so if we've got a reversible reaction like this, where this represents our reactants and this represents our products, this is the general equation for K. But if we were to figure it out for a more complex kind of a equation, this is the general way that we write out K, where K represents the concentration of one of our products, so that's going to be C, raised to the power of the number of moles that we have of that chemical. Likewise, it's the concentration of D raised to the power, and that power is going to be the moles of this product as well. Likewise, we're going to put the reactants on the bottom. It's simply the concentration raised to the mole. So what am I talking about? Let me show you an example of that. If this is our equation right here, this is going to be our equilibrium constant. And so what do we have? Well, here's going to be our products on the top. So it's going to be the concentration of water right here raised to the 2 power, because we have 2 moles out in front of that. Likewise, we've got nitrogen gas raised to the 1 power because we only have 1 mole of that. We're then going to put our reactants in the bottom. Likewise, both of these are raised to the 2nd power because each of those have 2 moles. Now, if I were to give you that reversible phosgene reaction, could you write the equilibrium constant for that? What's our K value going to be equal to? It's simply going to equal to this. Well, each of these are raised to the 1 power because we have only 1 mole of each of these. So this would be our K value. Now, we can calculate K in the lab, and so at standard temperature and pressure, our phosgene is going to be this. This is going to be that value I showed you at the beginning, 4.57 times 10 to the 9th. What does that mean? We're going to have way more of this product than we do the reactant at that given point. In other words, you could write this number over 1 on the bottom, and it's going to show you how many of them are going to be the phosgene. Now, if we were to change the temperature, we can actually change that K value. If I change that temperature to 200 degrees Celsius, so if I change it and make it a really high temperature, you can see that our K value is going to be much lower. What does that mean? It's going to be shifted back towards the left, and we're going to have way more of those reactants than we do products. Likewise, if we were to take this equation right here, where we've got nitrogen and oxygen, and we're converting that into nitrogen oxide, what would that look like? Our K value is going to be simply this. It's going to be raised to the 2nd power because we have 2 moles of this gas. What is our K value for this equation? It's going to be a really, really small value. What does that mean? That we're going to have way, way more reactants concentration-wise than products, and so it's going to be shifted way over here towards the left side. Now, what if I were to increase temperature at this point? Let's say I were to have a strike of lightning, that's actually going to raise our K value and it's going to push it over towards the right side. Now we know that in the atmosphere we have nitrogen gas and we have oxygen gas, but if we had a K value that was really, really large at standard temperature and pressure, all of this would quickly be converted into nitrogen oxide, but we know that doesn't occur. It only occurs when you have a huge amount of energy, a huge amount of lightning. And so again, in summary, if our K value is ever greater than 1, that equation is going to move from the reactants to the product side. We're going to have way more products than we do reactants. If it's ever less than 1, then we're going to have the reverse is true. We're going to have way more reactants than we do products. And so did you learn to use the values of K to predict which chemicals we're going to have when it reaches equilibrium?